everybody. Welcome to the ICMAT Distinguished Lectures. So this is our first edition. This is going to be a series of events that we're going to have twice a year. The goal is to invite or to bring the most prestigious, the best mathematicians around, and the idea is to have two talks every edition. This event is an honor to have Charlie Fefferman. Antonio will introduce him in a moment. And then we have already been confirmed that Claire Wassan is going to come for the second edition in April 1st. So we will make the announcement shortly. So I hope you enjoy the meeting. And then it's not the best option to have Charlie in the US and not having him here. But anyway, we hope that soon you will be able to come to Madrid. So I'm gonna now give the microphone to Antonio that he will introduce you for this talk. Antonio. I guess that we can now see. Oops. Go ahead.
So, can I take out the mask?
Yes.
Okay. So, hi everybody. Hi Charlie.
Hi Antonio.
Okay. So it is surely a signal of a certain return to normality, finding myself here in the introduction of our speaker. That is a task that I have performed in many occasions in the past, without, believe me, having the opportunity of repeating myself or being bored. At the 70s of the past century, one has to emphasize Fefferman's achievement regarding Fourier series and his marvelous disproof of the disk multiplier conjecture using the properties of the so-called Kakeya set. But very quickly, the scenario changed, and the presentation have to mention his theorem characterizing local solvability of linear PDEs, the theory of wave packets, and the uncovering of the role of the uncertainty principle in microlocal analysis. The action, once more, move now to several complex variables, where Fefferman answered a well-established conjecture of Henri Poincaré about the smooth extension up to the boundary of biholomorphic maps between a strongly pseudo-convex domain in Cn. But then he got interested in the many body problems of quantum mechanics, namely stability of matter and the asymptotic expansion of the ground state energy of large atoms. In this way, opening a door for the mathematical understanding of the periodic table from first principle of quantum mechanics. And so on, together with several, let us say, sporadic excursion into the theory of neural network, financial mathematics, of the structure of nodal set in the eigenfunction of Laplace-Beltrami operator, M on O, we find Fefferman's important contribution to fluid mechanics with a strong influence in the mathematical production of our own institute, ICMAT. Finish, let us mention two areas of main activity which are the subject of today's talk, namely the basic analytical problem of how to extend properly function defined on an arbitrary, more or less arbitrary set of Rn to the whole Euclidean space, the so-called Whitney extension problems, and the fascinating mathematical question arising in the understanding of the dynamic of Bloch electron in graphene, or more ambitiously, how to develop mathematically from first principle the laws of solid-state physics. Along my many presentations of Charles Fefferman, I also have to mention prizes and honor, beginning with the Salam Prize, the Field Medal, and the Waterman Award of the 70s. It followed an impressive list of recognition, whose last member, if I am not wrong, was the Wolf Prize awarded to him in 2017. We can therefore conclude that Charlie Fefferman, having his main basis of operation located at Princeton University, has shown us the power of mathematical analysis and enjoys so far a rather successful, and I would also say happy, life and theory. Thank you. Charlie, it's your turn.
All right. Well, Antonio, thank you for that remarkable, generous introduction. Thank you all for the invitation. I hope you enjoy the talks. Now, I have to warn you, technology is my enemy. I sincerely hope that the connection survives throughout the two lectures. Let's get the slides up for the first one. There we go. Okay, now, all right, I'm going to be talking about my obsession over the last almost 20 years. And so, pardon me, I'm reusing slides from a previous conference. Okay, so let's start. Oh, please, I understand that the lecture is supposed to take 55 minutes. I don't want to go over. Please, somebody give me a 5-minute warning. Okay, so, okay, next slide, please. Okay, so this lecture, not these lectures, will discuss two closely related problems, interpolation and extension. Next slide, please. In interpolation, we're given a finite subset of Rn, E, and we're given a function f, let's say real valued on E, and the problem is to compute a more or less smoothest possible extension, capital F, defined on the whole Rn that agrees with little f on E. Next slide, please. Okay, so before E was finite, in the extension problem, E will probably be infinite. So f will be a real valued function on an arbitrary set E, given, and the problem is how to decide whether there exists a smooth function, capital F, on the whole Rn that agrees with the given little f. Next slide, please. Okay, in this first and only lecture on the subject, I'm going to state the main results, and subsequent lectures will not discuss the proofs or indicate further results. Next slide, please. Okay, let's get started. Next slide, please. All right, let's start with notations and definitions. Next slide. Okay, so X is our favorite Banach space of continuous functions on Rn. It might be Cm, the functions whose derivatives up to order m are continuous and bounded, or maybe Cm alpha, those Cm functions whose mth order derivatives are Holder of order alpha, or maybe the Sobolev space WMP of functions which together with their derivatives up to order m belong to LP. So we're going to use that Banach space to say what we mean by a smooth function. And I'm going to make the notational convention that any constants that are denoted by some version of the letter C will be constants that depend only on the choice of the space X used to measure smoothness, and not on the particular problem we're solving. Next slide, please. Okay, so for example, if X is the Sobolev space WMP of Rn, then any constant denoted with the letter C will depend only on the parameters m, n, and p. Next slide. Okay, so now suppose that E is finite. X of E is going to denote the space of all real valued functions on E, but with a norm that remembers that we're trying to extend functions to into the Banach space X. And so there on the slide is the definition of the norm of f in X of E. It's simply the inf of all the norms of all possible extensions where we measure the norm of an extension in our favorite space X. Notice that's an inf. Elementary examples show that the inf needn't be attained. It needn't be a minimum. And that motivates the next definition. Next slide. Okay, so suppose f is some function on E, And capital F is an extension, and A, notice not denoted by the letter C, A is a positive constant. F is an A-optimal extension of F if capital F agrees with little f on E, and furthermore, its norm is within a factor of capital A of the least possible, that is, of the inf. So we want to compute such things, and so our problems are, given the Banach space X, the set E, and the function F, we want to compute the order of magnitude of the norm, and we want to compute a C-optimal extension. Again, C-optimal means C depends only on the space X. Okay, now what exactly do those things mean? Next slide. Okay, to compute the order of magnitude of the norm means that we're going to compute some other number that I'm going to call the triple norm, with the property that that number that we can compute differs from the number we'd actually like to understand, which is the norm of f in x of e, by at most a constant factor, as on the slide. That's what it means to compute the order of magnitude of the norm. Next slide. Now, what does it mean to compute a function? Well, it means the following. So next slide. We're trying to compute a function in CM. We sit at a computer. We enter the data, the set E and the function f into the computer. The computer then grinds away performing one-time work. When it's done, it signals that it's ready to answer queries. Next slide. We can type in any query we like. A query consists of a point, x in Rn, and in response to a query x, the computer calculates the function f and its derivatives up to order m at that given point. And since our function capital F is only assumed to belong to Cm, that's all the information we could ask for at the point x. And so that's what it means to compute a function. All right, next slide, please. A technical point. The response to a query should depend only on the data we entered into the computer and on the point x. It is determined uniquely by, so the function we're computing is determined uniquely by the data. It does not depend on which queries we decide to address to the function, to the algorithm, sorry. Okay, next slide. Okay, now we don't want to wait forever for the answer, so we want efficient algorithms making minimal use of computer resources. Next slide. Okay, what are the relevant computer resources? Well, if you're computing a function, you want to know how many computer operations the one-time work will take. You want to know how many operations it will take to answer a query, and you want to know how much storage is used by the algorithm, the size of the RAM. Here, a computer operation means, let's say, adding two numbers together. And the size of the RAM, well, let's say one memory cell holds one real number or one integer. So there are three different computer resources, and it's normal when you're trying to optimize three different things to expect trade-offs. But in this case, we're lucky and we're going to optimize all of these simultaneously. Okay, next slide. Let's look at the trivial lower bounds on the computer resources used. So throughout this talk, whenever E is a finite set, capital N will always be the number of points of E. Now, the one-time work had better be at least capital N because we'd better read the problem. The query work is at least one because we had better answer the query. Actually, it might be nice also to read the query. And the memory used is greater than or equal to capital N because we had better remember the problem. So those are trivial lower bounds. Okay, that's for the computation of the function. And in computing the order of magnitude of the norm, that's just a single number. And so the relevant computer resources are simply the number of computer operations and the size of the RAM, number of memory cells. And we're going to optimize both simultaneously. Okay, next slide. Uh-oh. There, whoop, hello, next slide, please. Okay, yes. Now, a very important point I'd like to stress is that we're interested in algorithms that work for any finite set. If we allowed ourselves to some favorable geometric assumptions on the set E, for instance, if E looked anything like a lattice, life would be much, much simpler. And if you will excuse me, I'm getting a text. Okay. I'm going to answer the text, I'm sorry. Okay. Anyway, right. So if the set E looked anything like a lattice, life would be easier, but we want to deal with arbitrary finite E. Okay. So please, next slide. Okay. So let's look at some cases, some delicate cases where it isn't so easy. Okay. In the first case, our space X is going to be, let's say, C5 functions of the plane, and the set E on which our data, little f, will be defined, will be the red dots in the picture. I'm not going to tell you the function little f, but I'm going to ask, given a little f, how can we decide what should be the derivative in the vertical direction of our extension at the point z? And well, the thing is, if you look at this picture, you'll see that there's only one dot x that isn't really close to the horizontal axis. And so any information about vertical derivatives must come from comparing x with a nearby point like y. And that in turn, all right, if that tells you something about the vertical derivative, let's say at y, then with any luck, you will know something or other about the vertical derivative at z. The nasty point is that x and y need not be among the 100 points closest to z. And so any algorithm that determines the Taylor expansion of the extension at z based on the 100 closest points is bound to fail. By the way, as I zip through these slides, please feel free to ask questions. I don't want to snow anybody. Okay. Okay, next slide. Okay, example 2 is analogous. The only thing is that instead of lying close to the x-axis, these points lie close to this curve that I've drawn, which I imagine is the zero set of some polynomial whose degree is at most 4. The point about 4 is that we're working in C5. So the problem there is analogous to the previous problem. There's only one point x that doesn't lie incredibly close to the curve gamma, and that makes trouble. But remember, we're just given the red dots in the problem. Nobody tells us that the curve is there. And so any algorithm that deals with this case had better notice very quickly that this curve gamma is relevant to the problem and should then deal with that. Okay, and in the next example, next slide, please. In the next example, we're in 3 dimensions. X is, let's say, C5 of R3. E again consists of the red dots. And we've got an algebraic surface, and the red dots lie very close to that. And on the algebraic surface, there is an algebraic curve, and the dots lie quite close to that, but not as close as they do to sigma. But there is this one outlier dot that doesn't lie quite as close to gamma as the others. And so we have a hierarchy of things. We have the curve gamma and the algebraic surface sigma. Again, we're not given either of those when the problem is posed to us. We're given only the red dots, and we had better notice quickly that there is an algebraic surface sigma and an algebraic curve gamma, and we'd better deal with it. Okay, so those are delicate examples. Okay, next slide, please. Okay, the moral of the story is as on the slide. We had better decide quickly whether E lies close to the zero set of a polynomial of low degree. And if such polynomials exist, we'd better detect them and respond to them quickly. Okay, next slide. So real algebraic geometry enters the story. Next slide. All right, so what are the results? They depend on the space X. And for a long time, we're just going to be talking about Cm of Rn. So little m and little n are going to be fixed. Okay, next slide. So here's the theorem joint with Boas-Klartag. So we're working in the Banach space Cm of Rn, and we're given one of our extension problems. And so capital E is a finite. I'm sorry, did somebody have a question? No. Okay, capital E is a set with capital N elements. Little f is a real valued function on E. And the claim is that one can compute a C optimal extension using at most C n log n operations of one-time work, C log n operations to answer a query, and C n memory cells of RAM. Okay, that's very efficient, We can also compute the order of magnitude of the norm. That's the other thing we wanted to do. And that can be done using Cn log n operations of work and Cn memory cells of RAM. Okay, that's all very good news because those upper bounds on the required work and memory are all within a factor of log n of the trivial lower bounds. I don't have time to make the argument, and I don't have a rigorous proof or even a very careful statement, but I think it's very likely that the upper bounds that I posed are sharp. And so this algorithm always works, is completely efficient and handles the delicate cases. Okay, that sounds great for a practical problem. However, all right, next slide, please. Unfortunately, the algorithms are not at all practical because some of the constants that, that depend only on the space are nevertheless big constants. And if they're too big, then the result is not of practical use. This means that I would like very much to prove the same theorems, but with better constants. Okay, now the algorithms above are, all right, they're algorithms, but they are related to theorems. And these theorems come out of the study of Whitney's extension problem that I'd like to talk about next. So that's a question, a mathematical question rather than an algorithmic question. Okay, next slide. So here's Whitney's classical question from 1934. So we fix little m and little n. We are given some god-awful set, capital E, contained in Euclidean space Rn, and we're given some function phi defined on the set E. And the problem is, how can we decide whether phi extends to a function in Cm of Rn? So if such a function exists, let's call it capital F as before. Next slide. Well, if such a capital F exists, then we could ask how small we could take its norm in Cm. We can ask whether we can take that capital F to depend linearly on the function phi. And we can also ask what we can say about the derivatives, maybe of higher order of capital F at a point of E. So that was Whitney's classical question, set of questions from 1934. That problem has been solved in the early 2000s, and three big ideas were relevant. So I'd like to explain what they are. Next. Okay, the first was already due to Whitney, the Whitney extension theorem. So again, we fix little m and little n. We're given now, let's say, a compact set E in Rn. And for each point of E, we are given not just the value of a function, but we're given an nth degree polynomial, Px, which we hope is the Taylor polynomial of our unknown function capital F. And so Whitney asked, given such data, does there exist a function capital F in Cm whose nth degree Taylor polynomial at each point x of the set E is equal to the prescribed polynomial Px? That was the question. And Whitney's answer, next slide, is that the obvious necessary conditions just arising from Taylor's theorem are sufficient. Of course, if 2 points are close together, the Taylor polynomials at those 2 points of a nice smooth function had better be very close in some quantitative way. And Whitney spells it out and proves that if those conditions are satisfied, you can find the capital F. And it's a wonderful theorem which led to many things, but let's leave it at that. So that's one of the ingredients in the solution of Whitney's classical problem. Okay, next. The next lecture will not present the classical Whitney extension theorem. It will do something completely different. Okay, next. Okay, the second big idea for the solution of Whitney's problem is the idea of Glazer refinement. So Georges Glazer was a French mathematician in the 50s who solved Whitney's extension problem in the case of C1 of Rn using a geometric construction that he called the iterated paratangent bundle. Again, I heard some sound. Is anybody asking a question? No, okay. So that idea was further developed by Ed Bierstone, Pierre Millman, and Vyacheslav Pawlutsky for Cm for higher M in the case when the set E was subanalytic. Okay, and yet further development of that idea played a key role in the full solution of Whitney's extension problem in the general case, and we'll get back to that later in the talk, time permitting. Okay, next. Okay, the third ingredient And the one which is most closely related to the algorithmic stuff I talked about is a collection of finiteness principles. And the idea of finiteness principles goes back to the mathematicians Yuri Brudny and Pavel Schwarzman. Okay, next. Okay, so again, the connection of algorithms to Whitney's extension problem arises from a finiteness principle. So what is a finiteness principle? Well, next. Okay, so here's the theorem. So suppose we're given our usual little m and little n. Then there exists an integer constant k and a real constant c, and they depend only on little m and little n. Okay, they don't depend on the particular problem, but they only depend on those parameters, little m and little n, such that the following holds. Next slide. Suppose we have, as usual, a function on a finite set E. It's important that it be finite. So a function on a finite set E, and suppose that if you restrict the function to a k-point subset S, that has norm at most 1. So given any k-point subset S, if you restrict F to S and just try to find functions that agree with that restriction, you can always do that, and those extensions have CM norm at most 1. If that's true, then you can solve the whole extension problem with norm at most C. So in principle, to solve a great big extension problem, it's enough to look at all possible little extension problems. Okay, this theorem and several related results were conjectured by Brudny and Schwarzman in the 80s, although the results were proven much later. Okay, next. Schwarzman proved the analogous finiteness theorems with Cm replaced by C1 alpha. Okay, and the case alpha equals 1 is equivalent to the finiteness theorem for C2 by very simple reasoning, which will not be explained later. Okay, next. And the proof of C1 alpha was based on an idea called Lipschitz selection, which, time permitting, we will actually meet at the end of this talk. Okay, next. For the cases in which Pavel's proof applied, he actually got the optimal integer constant k, the size of the little sets you have to examine, and it's the curious number 3 times 2 to the power n minus 1 in dimension n. For example, for C2 of the plane, the number is 6, and so you have only to look at all 6-point subsets. Unfortunately, there are a lot of 6-point subsets of a great big set E. If E has n points, they're of the order of n to the 6th little subsets, which motivates the next refinement. Oops. Oh, okay. Next refinement will come in a minute. Okay, next slide. Okay. I should say that to treat Cm for m greater than 2 requires a different approach, unless there's some clever trick that everybody has missed so far. Okay, next. All right, so there are too many 6-point subsets of a given big set, and that motivates the refined finiteness theorem, which is joined by Boas and me, and underlies the interpolation algorithms. Okay, next. Okay, so all right, given little m and little n greater than or equal to 1, there exist constants depending only on little m and little n, such that the following holds. All right, now we're going to focus in on a particular problem. Usually a problem consists of a function f defined on a set E, but so far I'm not going to tell you the function f, I'm just going to tell you the set E. And so E is a big finite subset of Rn. It has capital N points, and given that subset, we can pick out a list of little subsets. Not all little subsets, but just a list, S1 through SL, such that, okay, next slide. L, the number of those little subsets, grows only linearly with the size of n, not n to the 6th, but constant times n. Each one of the sets S sub L is a little subset. It has at most k elements. And yet, and now we bring in the function f, for any function f on the set E, the norm of f in Cm of E is bounded by a constant times the maximum of the norms of the restrictions of f to all of those little subsets in our list. And furthermore, the sets themselves can be computed efficiently from E. Okay, next slide. Okay, One thing I don't like about this lecture is that I'm stating theorems and telling you no proofs. So let me give you a little glimmer of this proof, and I'm afraid that will be probably the only remark on any proofs of anything in this talk. So I'm going to use the notation Jx of f to denote the nth degree Taylor polynomial of f about x. J for jet, because if we were on a manifold, this thing would be a jet. Script P is going to be the vector space of all real nth degree polynomials on Rn. Okay, next slide. Okay, now we're going to ask just the right question, which will make it possible to make progress on proving the theorem and making the algorithms. So the key question is, suppose there exists a function in Cm with a given upper bound, capital M, for its norm. And suppose that this capital F is an extension of little f. So our extension, so our problem has a solution and we have a bound for its norm. Under those conditions, what can we say about the Taylor polynomial or jet of that function capital F at some given point x? That's the question. To formalize the question, I'm going to make a definition. So given a little f defined on E as usual, given a point x in Rn, and given a positive number m, let's define gamma of xm to be the set of all Taylor polynomials at the given point x of functions f which agree with little f on E and have Cm norm at most capital M. Now that set is obviously convex because you can take one half of one interpolant plus one half of another interpolant and it's still an interpolant. So that set is obviously convex. It might be empty. If we have been greedy and picked capital M too small, maybe there will be no interpolants. So this gamma is an interesting object. It's a possibly empty convex set. Okay, next slide. The real algebraic geometry that I talked about before is encoded in the size and shape of the convex sets gamma of xm. Next slide. In particular, if E is close to the set where some polynomial is 0, then the gamma is very long in the direction P. P is a polynomial, so it's a vector in the space of polynomials. And so it gives rise to a direction, and the set gamma is long in that direction. And that remark is easy from untangling the definitions, but at the rate I'm going, I think you have you don't have time to untangle the definitions, but I promise that it's clear, or should be clear, or would be clear if you had time. Okay, next. Okay, so to prove the refined finiteness theorem for Cm of Rn, we first understand the approximate size and shape of these gammas, and then we use the information on the gammas to compute an f with controlled norm that extends our function little f on E. Okay, so that's a little hint. And so these gammas and their close relatives that I won't define in this talk, called sigmas, will play a fundamental role in all our results. Okay, next. Here's a cute application, I find it cute anyway, of the refined finiteness theorem, removing outliers. Okay, next. Okay, so let's take a function on a finite set E, and we're going to look for a small subset S in E, such that if we remove that set S, suddenly it becomes much easier to interpolate. So S will be the outliers. Imagine an experimentalist has performed an experiment and gotten lots of data, but a few of the results are garbage because something went wrong with the machinery. All right, how do we find outliers and how do we discard them? Next slide. Okay, here's a simple 1D example. Imagine that your job is to draw a graph of a function of one variable that passes through all the red and blue dots. That function is going to be pretty wild, but if you just remove the 3 red dots, then there is a much nicer function that passes through all the blue dots. That's the idea. So we want to find the red dots. Next slide. Okay, so the theorem is that it's possible to order the set, to enumerate the set as a first element, a second element, and so on, through the nth element in such a way that, let's say, the 53 worst offenders in the set E are simply the first 53 elements in the enumeration. So more precisely, given any number z less than or equal to n, if we look at the set SZ consisting of the first Z elements in the enumeration, it's a reasonable candidate for the trash can for the following reason. Okay, next slide. If you're given any set that you might be tempted to discard, and if that set contains at most a constant times Z, small constant times Z number of points, and you try discarding that number of points, you won't do much better than just discarding SZ, in the sense that the norm that you get by discarding SZ is less than or equal to a constant times the norm that you get by discarding S. And moreover, this enumeration can be computed in polynomial time. And the proof of that, which I don't have time to show you, or the way the algorithm works, makes use of the refined finiteness theorem. Okay, next slide. Okay, sketch of the algorithm, no time. Next slide. Okay, all right, so I've been talking about Cm of Rn, and I've been talking about finite sets. Completely analogous properties hold for Cm alpha. So let's not spend more time on Cm alpha. Next slide. Let's talk now about Sobolev spaces. This is joint work with Aryeh Israel and Kevin Luley. Next slide. So we're going to be working either in the inhomogeneous Sobolev space WMP of Rn with the norm given on the slide, namely the sum of the LP norms of all the derivatives of f up to order m, or the homogeneous Sobolev space, which has the semi-norm in which you simply take the LP norms of the highest order derivatives and ignore the others. So the homogeneous Sobolev space is, of course, not strictly speaking a Banach space, because there are things with zero norms. Polynomials of low degree have zero norm. Never mind. Okay, next. Okay, now it's important that we deal with spaces of continuous functions, because we're looking at, right, our problems involve the values of functions at a point. And if our function is, let's say, only defined almost everywhere, then we can't talk about its value at a point. So, all right, our Sobolev spaces had better consist of continuous functions. That means that P is greater than n over m. N is the dimension, m is the number of derivatives. But we're going to make a stronger assumption. We're going to assume that P is greater than the dimension n, in which case the Sobolev space actually embeds in Cm-1. All the derivatives except the highest order ones are already continuous. Okay, so that's our standing assumption. For any subset E, not necessarily finite, X of E is going to be just the set of all restrictions to E of functions in the Sobolev space. So X of E consists of all functions on E that can be extended. And the natural norm or semi-norm in X of E of a given function f on E is given on the slide. It's simply the inf of the Sobolev norms of all possible extensions. Now, of course, if the set E is finite, X of E consists of all real valued functions. You can extend any function from a finite set to a very smooth extension on all of Rn, but we still have to understand the norm of f in X of E in case E is finite. And if E is infinite, we don't even know whether f belongs to X of E, and that already is a question. Okay, next slide. Remember the convention that constants denoted by C depend only on the choice of X, and so here they depend only on little m, little n, and P. Next. Okay, so the first theorem about Sobolev spaces is that for any set E in Rn, there is a linear extension operator. That is, there is a linear map from this X of E into the Sobolev space X with the two properties in the box. First of all, TF agrees with F on E, so TF is an extension of E, and the norm of T as an operator from X of E to X is bounded by a constant C. So that's the first theorem. Okay, next slide. Now suppose that E is finite. Let's say E contains capital N elements. Then a linear extension operator can be computed efficiently. A precise statement not to follow in the next lecture. So you'll be spared the details of exactly what it means, but in some sense, an efficient computation produces the linear extension operator. Okay, next. And that allows us to compute C-optimal extensions of a given function by simply applying that linear extension operator. And again, we can compute the extension using C n log n one-time work, C log n query work, and C n memory cells of RAM, as in the CM case. And so the details of that are much more formidable than in the CM case, which are already no joke, but it works. Okay, onward. Next slide, please. Okay, now there's also a formula for at least the order of magnitude of the norm. So given a finite set with capital N elements, there is a finite list of linear functionals on X of E with the following properties. Next slide. So first of all, the number of those linear functionals is at most a constant times the number of points of E. And secondly, if we evaluate those linear functionals on a given function F, and if we sum the pth powers of those and take the pth root and call that the triple norm, then the triple norm is comparable to the norm of F in X of E. And so that means that these semi-norms allow us to compute the order of magnitude of the norm of a given function in X of E. Next slide. Moreover, the X's, those functionals have a sparse structure so that if I give you a function F, you can compute all of those functionals, and therefore the order of magnitude of the norm of F using at most C times N computer operations, assuming that the functionals have been computed. So it's very good to know these functionals, because then you can compute the norm of a function basically as quickly as you can read the function. Okay, so we want to compute these X's. Next slide. And furthermore, the X's themselves can be computed from the set E using n log n work and constant n memory cells of RAM, and that's very likely optimal. Okay, next slide. Now remember, all of this has assumed that P is greater than n. Back when the team was working on this problem, we thought, okay, let's do that case, and then let's go back and see what happens if P is less than or equal to n, and it will be basically the same, just a little more work. That couldn't be more wrong. It's a different world. A team is working on it now, and we're very, very confused and need ideas. So if P is less than or equal to n, this problem is completely open. Okay, next slide. All right, now I'd like to return to CM of E, but I'd like to look at what happens when E is infinite. Next slide. So let's recall in particular Whitney's problem that got this whole subject started. So E is a given, probably infinite, probably disgusting set in Rn. We're given a function phi defined on E. We're given a number m. And the question is, how can we decide whether there exists a function capital F in Cm that agrees with the given phi on E? Next slide. Okay, now we're going to solve Whitney's problem. And in order to solve Whitney's problem, we first have to generalize it. And in a few minutes, we'll see why that's true. Next slide, please. Okay, I need a little more notation. Remember that Jx of F, the jet of X, is the mth degree Taylor polynomial of a function f at x, and script p is the vector space of all such. Okay, now there is a natural multiplication on Taylor polynomials, and I'm denoting it by dot sub x. So p dot sub xq is simply the jet at x of pq. Pardon me. The significance of that is that the jet at x of the product of two functions is equal to the product of their jets with respect to this operation dot sub x. So this is the jet product. And when I say jet, again, I just mean Taylor polynomial. Okay, and so Rx is the vector space script p, just of polynomials of degree at most m, endowed with this particular multiplication dot sub x. And so that is the ring of m jets at x. As x varies, of course, all these rings are isomorphic, but they're not identical, and it's going to be convenient to keep the subscript x. Okay, next. All right, so we're going to generalize Whitney's problem in order to solve it. Here's the generalized problem. Okay, given a compact set E in Rn, before E was arbitrary, but it's trivial to reduce to the compact case. So given a compact set E in Rn, suppose that for each x in E, we are given this affine subspace h of x sitting inside Rx. It is a translate of an ideal I of x by an element fx in the ring. And so since I passed an exam in algebra 50 some years ago, I can say that h of x is a coset of an ideal, okay? And so for each x, we are given such an object, h of x, a coset of an ideal in the ring R sub x. Next slide. The problem is to decide whether there exists a function capital F in Cm whose jet at each point of the set E belongs to that particular affine space H of x. That's the generalized problem. I'm going to call this script H a bundle. I'm sorry, so the script H is the collection of all those H of x's. That's a bundle. H of x at a given point x is going to be the fiber, and a function capital F is going to be a section if its jet belongs to the given fiber for each point of E. Okay, and so in that language, next slide. A little more language. If we have two different bundles over the same base, and if the fibers of one are always contained in the corresponding fibers of the other, then one is the subbundle of the other, and we write it with a containment sign as on the slide. Okay, that's the jargon. Okay, next slide. So given that jargon, we can then phrase the generalized Whitney problem as, how can we decide whether a given bundle has a section? Okay, now I should try to convince you that the generalized Whitney problem is a generalization of the Whitney problem. So suppose we're given a function phi defined on our compact set E. For each x, let's take, so for each x in E, f of x is going to be the constant polynomial whose value at all points is phi of x. And so that's a polynomial of degree 0, so that's an element of script p. And I of x is going to be the ideal in the ring Rx consisting of all polynomials that vanish at x. And we're going to take h of x to be f of x plus I of x, the coset, and so h of x consists of all polynomials whose value at x is equal to phi of x. Okay, next. Okay, you can check that collection of h's is a bundle, and you can check just by chasing down the definition, the definitions that a function in Cm is a section of that bundle if and only if its value at each point of the set E is the prescribed value phi of x. And so the question, is there a Cm function that agrees with phi on E, is equivalent to the question, does this particular bundle have a section? And what we're going to do is to decide whether an arbitrary bundle has a section. Next slide. Next slide. Thanks. Okay, so let's solve a generalized Whitney problem and talk about how to look at bundles and see whether they have sections. Next slide. Okay, it's convenient to make a small, very strange looking change in the definition of a bundle. I'm going to allow the empty set as a fiber at any given point. Next slide, we'll see why. So a bundle is now going to be defined as a collection of h of x's parameterized by the points of E. E is a compact set, where for each point x, either h of x is the sort of thing it was before, or the empty set, okay? Of course, if h has any empty fibers, it has no sections, because to be a section, the jet has to belong to the fiber, and if the fiber is empty, that's highly unlikely. Next slide. Okay, now the key idea following Glazer and Bierstone, Millman, and Pawlutsky is to define an operation on bundles, which is called Glazer refinement. Next slide. Okay, so given a bundle, as on the slide, we produce its Glazer refinement, which is another bundle over the same base. It's written with a tilde. We give the definition in a later lecture. Well, the later lecture won't occur, so I'll skip the definition. It's not terribly complicated. It would take, I don't know, 5 or 10 minutes, but we don't have 5 or 10 minutes, so I'm sorry. But what I'm going to do is just tell you what it does. Okay, next slide. So first of all, the Glazer refinement H tilde is a subbundle of H. So each fiber has maybe less stuff in it. However, every section of H is already a section of H tilde. And so from the point of view of deciding whether there are sections, the stuff that we have thrown away from H to produce H tilde is irrelevant. Furthermore, H tilde can be computed from H by doing linear algebra in fixed dimension and taking a limit. I promise you that that's true. You can't possibly check it because I didn't give you the definition of H tilde. Let's move on. Okay, so therefore, again, if we want to know whether a given bundle H has a section, we may replace that bundle by its Glazer refinement. And we have made progress by discarding junk from the original bundle. Next slide. Well, we can do that over and over again. So we can define iterated Glazer refinements. If you're given a bundle H, you set H0 equal to H. You then set H1 equal to the Glazer refinement of H0, and H2 equal to the Glazer refinement of H1, and H3 equal to the Glazer refinement of H2, and so on. And so we have iterated Glazer refinements. And they are getting smaller and smaller, as shown on the slide. And yet they have the same sections as the original bundle. And we can, for any particular L, we can compute them. Okay, so we're making progress. Next slide. The process stabilizes at some point L star. So after we do this a fixed number of times, depending only on M and N in the space Cm of Rn, after a fixed number of times, this process stabilizes, and the Glazer refinement of HL star is HL star itself, and then you just repeated Glazer refinement just produces the same thing over and over again. And so let's say H star is that H sub L star, that is the stable Glazer refinement of a bundle. And so, next slide. The theorem is that, any given bundle has a section if and only if its stable Glazer refinement has no empty fibers. Of course, if the stable Glazer refinement has any empty fibers, then it has no sections. And since H star and H have the same sections, H has no sections. So that direction is trivial. But the other direction is not trivial. And so the only obstruction to H having a section is we calculate H star, we make sure it has no empty fibers, and that's the solution to the generalized Whitney problem, and therefore the solution to the original Whitney problem. Okay, next slide. An application at the border between analysis and geometry. I have the sinking feeling that that this lecture would run over if I gave that. Let's see what time it is. Oh my God, am I already over time? Hello? Hello? Could somebody tell me, please? It's already 10 o'clock. I think I should have finished.
It's fine. We started a little bit later, so you can.
Oh, okay. But let's skip over all of these slides until you come to Lipschitz, until we come to selection problems. So just go through lots of slides. Continue. Thank you. Continue. Stop. Okay, there. I would like to say something about selection problems, either in CM or Lipschitz, joint work with Aryeh Israel and Kevin Lully, and joint work with Pavel Schwartzman. Next slide. So here's the CM selection problem. As usual, we have little m and little n, but now we also have an integer d, and we're given a finite subset of Rn. And for each point x in E, we are now given a convex set K of x sitting in Rd. And we want to find a selection of that family of convex sets, and it is a map from Rn to Rd such that at any given point x of E, the value capital F of x belongs to the set K of x. I'm going to call K of x the target. So whereas before, for each point x of E, we're given a function value and our capital F has to take that function value. Now instead, we're given for each point of E, we're given a convex target, and our capital F has to land in the target. Okay, and we want such an F to be in CM. Okay, next slide. So how small can we take the CM norm of a CM selection? Can we compute a selection with CM norm as small as possible up to a constant factor? So this is a generalization of the previous set of problems in which we require that our capital F agree only approximately with little f in the sense of those convex sets. Next slide. Here's a simple one-dimensional example. The set E consists of the blue dots on the x-axis. Above each blue dot on the x-axis is a green horizontal line, which is its target, and we want the graph of, let's say, a C2 or C3 function to pass through all the targets. So that's a simple one-dimensional example. Okay, next. Okay, now there is a finiteness theorem completely analogous to the previous ones, except that it's in the context of extension problems. And so if you're given any CM extension problem, and if you can solve all little subsets of the extension problem, then you can solve the whole extension problem. Next slide. Okay, I want to give a proper credit to Brudny and Schwartzman, who deserve a lot of proper credit, but I don't have time to explain. Next slide. Okay, now the finiteness theorem that I just stated is analogous to the one for interpolation, and that problem gave rise to an efficient algorithm. And so one could hope that there is an efficient algorithm for the selection problem, but we don't have one. Next, but we'd like to find one. Next slide. Okay. However, with joint work with Bernat Guillen-Pegueroles, we can do approximate CM selection in which we allow the convex sets K of X to be dilated slightly about their center of mass. I don't have time to explain, so please let's zip past a couple of, yeah, keep going. Keep going. Okay. Last problem I'd like to discuss is Lipschitz selection. We've always been in Rn until now, but now we're going to be in a metric space X. And now, given each point of the metric space, we're given a compact convex set K of X in Rd. And what we want is a Lipschitz map from X to Rd, such that for each point X of the metric space, the value of that map F is in the target K of X. Next slide. And there is a finiteness theorem for that. It is joint work with Pavel Schwartzman. And again, it says that if you can solve any little subset, a little subproblem, then you can solve the whole problem. And in this particular case, we can actually specify the exact size of the little subproblems. We have to pick out 2 to the power d points of the space, of the metric space X, and that's best possible. Next slide. Okay, can we say anything useful about computing Lipschitz selection? So is there an algorithmic version of that? Okay, finally, many omitted topics. How about we try to fit manifolds and not just graphs of functions to data? In some cases, for some spaces, let's say for Sobolev spaces, there are extensions with least possible norm, not just least possible up to a factor C. What can we say about them? What can we say about C infinity selections? Next slide. Okay, what about problems with constraints like non-negative functions, maps into the unit ball, convex functions? A lot has been done about that. I would have liked to give proper credit, but no time. It would be great to obtain practical algorithms by making some of these constants C smaller. And there's a whole different subject, extending functions from open subsets to all of Rn, retaining smoothness, and that's a different world. Okay, I think I've gone over time. Thank you for your patience. Let's stop here. Done. Thanks.
Charlie, so is there any question here in the audience? If not, we give time. I'll go with the microphone.
Hello. So can you prove analogous optimal extension theorems for real analytic functions? For example, considering the supremum norm is an analytic band?
Oh, that's an excellent question. And the answer is absolutely clear. No. Okay, our methods make crucial use of partitions of unity, and anything real analytic is not going to work.
So
Sorry.
Any other question or comment?
Hi, Charlie.
Hi.
You mentioned that this problem, you have been working in this problem for the last 20 years or so.
Yes.
Okay. If I recall, in your previous work many years ago, you used to concentrate on a difficult, very difficult question in the field, solve it, and then move quickly to why?
Oh my God! Why did I stay with this for 20 years? Okay.
I can see that the nature of this interesting problem is probably different from the other. But from your point of view, can you tell us why?
Okay.
Your attitude.
Okay. So the first, I think for me the problem kept changing. So the first version of the problem was just the completely classical Whitney extension problem. Okay, and then that got solved. But along the way, I wondered, can you compute anything? And so that was a different version of the problem. And then I thought, okay, so this is CM, but all of these techniques are completely are completely dependent on the fact that the norm is defined by a soup. What are we going to do with other spaces where the norm is defined by an integral? Sobolev spaces are natural, and there's no hope, or is there? And so that was the next version of the problem. And then I guess let's see, I heard from Schwarzman about the problem of Lipschitz selection, and it seemed to me that the techniques, everything I knew was in Rn, and so I wondered, could one do anything in a general metric space? And then I thought, okay, well, let's clean up the p less than n for Sobolev spaces. Oops, my God, it's much harder than I thought, and I don't know if I'll ever do it. So that's the narrative of how I came to stay interested in the problem. But of course, that could have happened with the previous problems also. So why did this one hold my attention for a long time? I don't know.
Yeah, somehow in the other cases, you solve difficult problem asked by other people, Poincaré and so on.
Yeah.
You are creating your own flow of interesting questions.
Well, thank you. So, okay, I guess that's the kind way to put it. Thank you. I guess the unkind way to put it is that I'm stuck on the same problems for 20 years.
Okay, maybe we can resume our meeting today. So the second talk is math of graphene and related materials. So Charlie, go ahead.
Okay, thanks. So, okay, let's see. Well, let's go right to the next slide. Next slide, please. Next slide, please. Oh, we have technical problems.
Hold on a second. We have. Just a second, because now.
Sure.
Okay, hold on a second. Intentará help? Okay.
Oh, okay. So this is joint work with the people you see on the slide. Javi Gomez Serrano, an alum of the ICMAT, is starting to get involved. Also, there have been very preliminary discussions with Antonio Cordova about magnetic fields. We won't get to that today. That's at a very early stage. Okay, let's go on. Okay, So what we're going to do is study what's called the one electron model of graphene. So those are Schrödinger operators where the potential lives on the plane and is periodic with respect to a very special lattice called the honeycomb lattice. Okay, next slide. Okay, now the mathematical theorems are going to justify some of the most basic properties of graphene that physicists have known for a long time, but I think they will touch on a couple of points that aren't so well known. But the main theorems are going to be about Dirac points and edge states. Okay, next slide. There are well-known heuristic calculations that apply when the potential is either very strong or very weak. If it's very weak, then it's just, you can regard it as a perturbation of the Laplacian in the plane. And if it's very strong, there are other things. We'll get to them later in the talk. Okay, but next slide. Okay, we're going to justify the heuristic calculations. That's a standard thing to do in mathematical physics. But also we're going to discuss what happens when the potential is not very strong and not very weak. What can we prove when the potential is medium-sized? Okay, next slide. Okay, here's what graphene looks like. So the dots are supposed to be carbon atoms, and they're arranged in this interesting pattern around the vertices of the tiling of the plane by regular hexagons. Well, this is Charlie's attempt to draw regular hexagons. Notice that there are red dots and green dots, and those are called A points and B points. Okay, next. Okay, if you just look at the red dots and pick out one of them, let's say, as the origin, then these dots form a lattice spanned by two vectors, V1 and V2, as shown on the slide. My drawing isn't very good. They should be two sides of an equilateral triangle. And so that lattice is the honeycomb lattice, lambda or lambda H. Okay, next slide. Okay, now we're going to be doing Fourier analysis. So we're also interested in the dual lattice, which is lambda H star. And those are all vectors whose dot products with anything in the honeycomb lattice is a multiple of 2 pi. And so here on the slide, you can see two vectors that generate the dual lattice. Okay, next. Okay, now, okay, the Brillouin zone is a fundamental domain for R2, for the plane modulo the dual lattice. It's simply the set of points in the plane which are closer to the origin than to any other point of the dual lattice. And so if you look at the dots around the rim of this slide, you will see some vectors in the dual lattice and the hexagon. The interior of that hexagon is the Brillouin zone, and there are the particular points of great interest, the vertices of the Brillouin zone, and the one at the top is called K, and the one at the bottom is called K prime. Okay, next. Okay, now the honeycomb lattice and the dual lattice and the Brillouin zone and the red dots and the green dots are all invariant under a 120-degree rotation R. Next slide. And a basic observation that makes graphene do what it does is that this special point K, the top of the Brillouin zone, is not in the dual lattice, but it differs from RK and R star and R squared K by vectors in the dual lattice, as shown on the slide. Okay, that's a very special circumstance, and here you see it spelled out. There's K and there's RK, and notice that K and RK differ by the vector K1 in the dual lattice, and similarly R squared K differs by from K by the vector K2, which is in the dual lattice. Okay, next. Okay, so now we're going to do undergraduate solid state physics, with namely elementary Fourier analysis of the action of lattice translations on wave functions for our Schrödinger operator. And those are called Bloch modes. Okay, next slide. So for any K in the Brillouin zone, a K pseudo-periodic wave function is a wave function which has the property that if you translate it by a vector v in the honeycomb lattice, it simply multiplies by a phase as shown on the slide. So for example, if k is 0, this would be a periodic function. And if k is not 0, then it's periodic except for this funny phase. This k is called a quasi-momentum, okay? L2k is the Hilbert space of all k quasi-periodic or pseudo-periodic wave functions, locally L2, with a natural inner product that I'm not going to spend time writing down, okay? Now, all right, the Fourier analysis relevant here is that every L2 function on the plane can be written as an integral over the Brillouin zone of k pseudo-periodic functions, the integral with respect to k varying over the Brillouin zone. Okay, next slide. And furthermore, the Hamiltonian minus Laplacian plus v maps L2k to itself for each k. And that means that the spectral theory of H, of our Hamiltonian, reduces to the spectral theory of HK, where HK is the restriction of H to a particular LK. And so K is going to vary over the Brillouin zone. And for each K, we have the Hamiltonian HK. We're going to do its spectral theory, and then we're going to vary K. And that's the spectral theory of H. Next slide. Okay, and so for each K, HK has a discrete spectrum. Its eigenvalues are called E1 of K, E2 of K, and so on in increasing order. They tend to infinity. And the corresponding eigenfunctions are called Psi1 of xk, Psi2 of xk, and so on. Next slide. Okay, now for each particular nu, let's say nu is 1, the numbers 1, 2, and 3 are particularly interesting. We could look at the nth eigenvalue of this Hamiltonian as a function of k in the Brillouin zone, and those are called the dispersion relations, and their graphs are called dispersion surfaces. Okay, so E nu of k is the guy we're interested in. Okay, next slide. Okay, now it happens that the dispersion surfaces for graphene have Dirac points. So what are they? Okay, so there are two successive eigenvalues. So there's, let's say, nu0 minus 1 and nu0. And as a function of k, if you look at them, well, they are as on the slide. Capital K is this special quasi-momentum, the upper corner of the Brillouin zone. And for little k near capital K, the graphs of these two dispersion relations each look like a cone. One cone is pointing up, and one cone is pointing down, and together they form a double cone. And it's not quite a perfect double cone because there are these correction terms, little o of absolute K minus capital K, but asymptotically, it is a double cone. And so these are called conical points or diabolical points. The connection to the devil I'm not sure of, but they are called diabolical points. And this number lambda 0 is a non-zero coefficient called the Fermi velocity. That's what a Dirac point is. Okay, next slide. Now, what does a Dirac point do? Well, a wave packet with quasi-momentum near K travels as a relativistic free particle approximately for a long time. So that double cone, that dispersion relation, is characteristic of a relativistic free particle in 2 dimensions. And so it means that even though graphene is full of atoms, nevertheless, under the right conditions, an electron can simply pass through, can simply pass along a sheet of graphene as if it were in empty 2-dimensional space. Next slide. Okay, so those are, that's the setup. Well, all right, let's now try to formulate a theorem. So I want to describe what assumptions I'm making on the potentials. So VH is, so these are called honeycomb potentials. Out of sheer laziness, we're going to take C infinity functions, but we could allow Coulomb singularities. It wouldn't be significant. I mean, the changes would be minor. Okay, what we want is that the potential should be translation invariant under the honeycomb. It should be even. That means we have to pick out the right origin. Let's pick out the center of one of the hexagons as the origin. And so it is even, and it is also invariant under a rotation by 120 degrees, because the whole, I mean, graphene is supposed to be invariant under 120 degree rotation. So those are the assumptions on the potentials. Okay, notice so far V could be, for example, 0. Okay, so the first theorem is the following. Suppose that we have a honeycomb potential, and suppose that this particular Fourier coefficient described on, written on the slide is not 0. So we have excluded the 0 potential. Okay, then let's look at the Hamiltonian as shown on the slide, minus Laplacian plus a coupling constant lambda times V. Okay, that Hamiltonian has a Dirac point at quasi-momentum capital K for all lambda, for all coupling constants outside a discrete set E. Okay, so remember, one of our jobs in doing the mathematics of graphene is to try to see what happens if V is medium-sized, neither large nor small. Here it is, V is neither large nor small, and we're just excluding a discrete set of anomalous coupling constants. What about that discrete set? Okay, next slide. Well, for a large class of honeycomb potentials V, there exists some a positive coupling constant lambda tilde with the property that what you get is not a Dirac cone where 2 dispersion surfaces meet, but rather 3 dispersion surfaces meet. The first 3, so E1, E2, and E3, the first 3 dispersion surfaces at quasi-momentum capital K, that distinguished point, are all the same, and that happens for some carefully selected lambda tilde. So the discrete set isn't just empty, it's there. Okay, next slide. Okay, that has the implication that wave packets propagate almost as relativistic free particles for a long time. And so there's going to be a precise theorem that says that. So we're going to fix a V as in that first theorem, and we're going to fix a coupling constant lambda, which is not in that bad set script E. And we want to solve the time-dependent Schrödinger equation as on the slide. And let's skip the next few slides. I would like to, okay. There is a theorem that says that for a long time, there are wave packets modulated by, there are wave packets that propagate as free particles approximately for a long time. And so there's a precise statement of that, and we have a proof. Okay, let's keep going. Keep going again. There's theorem 2 saying what I just said, but let's not worry about the exact statement. Okay, now these theorems persist under small changes in the potential and also small deformations of the honeycomb lattice. So let me be a little bit careful. The potential has to be even. So that has to be exactly maintained, but the rest of the assumptions can be perturbed a bit. And the result of that is the following. Okay, next slide. So instead of the double Dirac cone being as in the equations in the first box, they are rather as on the second box. So what is happening is that now 2 successive dispersion relations touch at a point, and they form a sort of tilted elliptical cone. So notice we have, first of all, E0 tilde. So that's just the constant energy at which the 2 dispersion relations touch. But then we have the linear terms B0 dot K minus K tilde. K tilde is the point at which the Dirac cone forms, and it is no longer exactly K. It has been perturbed away. So there is a linear term, and so the cones are a little bit tilted. And furthermore, instead of the absolute value of K minus capital K, instead we have the square root of some positive definite quadratic form in K minus capital K. And so we have tilted 2 tilted elliptical cones that meet not at quasi-momentum capital K, but at a nearby capital K tilde. That's what happens when you perturb. Okay, it's nice that these things are robust because in the real world, perfection seldom happens. Okay, next. Okay, if V is no longer even, then generically there are no longer Dirac points, and here's how things perturb. So on the left-hand side, imagine V is exactly even and we get our Dirac double cone. But if V is close to even, but not exactly even, you get these tips of large curvature, but nevertheless C infinity. And they do not exactly touch. And so no Dirac points. Okay, next. Okay, so that, at least for the moment, is what we have to say about a sheet of graphene. Now let's take the sheet of graphene and cut it with a knife. So we have, instead of carbon atoms located at every vertex of the tiling of the plane by hexagons, we cut the plane with a knife along a straight line, thus dividing the plane into two half planes, and we throw away all of the carbon atoms in one half plane, and we keep the carbon atoms in the other, and that is a sharply terminated honeycomb structure. There is another interesting kind of edge state for something called a domain wall, but today I'm not going to discuss it. Okay, so next slide. Okay, so let's look at the edges. Of course, if you have just a line in the plane, it doesn't matter which line you have. But if there's a hexagonal tiling of the plane that is fixed in the background, it matters a lot which line you have. Next slide, please. Okay, so here are some classic examples of edges. So this one is called the zigzag edge. So I've drawn the blue straight line. It's supposed to be a straight line, and everything lying below that straight line, all of those carbon atoms are still there. I've only drawn the ones close to the edge, but all of the ones lying below the blue line are still there, and all of the ones above the blue line are empty, and there is just vacuum. Okay, so the electrons can still go there, but they will find no carbon nuclei. Okay, next slide. Here is the bearded zigzag edge, so-called, in which now the blue line has been moved parallel to itself, same direction, but it's been moved, and now the zigzag has grown a beard. Okay, and so this is the picture. Okay, and I'd like to give a third example. It's called the armchair. So next slide. Okay, and now the blue line is horizontal, and this is called the armchair because if you imagine a line, forget about the blue line, just move between the green dots and the red dots, moving from left to right, you will see some armchairs in which one might sit down if one were small enough. And so that's the armchair edge. But of course, there are lots of edges. So next slide. Here's some other rational edge. So by a rational edge, I mean a straight line that passes through at least two, and therefore infinitely many of the nuclei in the graphene structure. So this is some other rational edge, not one of the three classic examples. And furthermore, next slide, there are irrational edges. There are plenty of straight lines that pass through, let's say, one of the nuclei of the structure and no others. Okay, next slide. Okay, so those are the terminated structures. Now let's talk about the potentials. They're not quite as general as in the previous discussion. They're going to be superpositions of atomic potentials. So let's first fix an atomic potential, which is variously going to be called V sub A or V sub 0. The notation is going to be a little wobbly. For the moment, it's called V sub A of X, and it is simply a potential on R2. And we think of it as the potential of a single atom centered at the origin. Okay, next slide. So here are the assumptions. It's negative, it's between, or it's non-positive, it's between 0 and -1. Again, that's out of laziness. We could give it a Coulomb singularity, it wouldn't matter. Our atomic potential is going to be supported in a small ball, a small disk about the origin. And the radius of this disk should be less than less than or equal to 0.3 times the distance between nearest neighbors in the honeycomb. You might think that 0.3 is really 0.33333, 1/3, but no, it is 0.3. The potential is assumed to be invariant under a 60-degree rotation about the origin that will make it both even and invariant under a 120-degree rotation as before. Okay, so those are our assumptions on the atomic potential. Next slide. Okay, now from the atomic potential, we make an atomic Hamiltonian, and that's minus Laplacian plus lambda squared VA. Lambda is a coupling constant. I'm multiplying it now by lambda squared instead of lambda. Who cares? Lambda squared. Lambda is going now to be a large coupling constant. So we're in the regime of large coupling constants. And I'm going to make the following assumptions about the atomic Hamiltonian. So first of all, its lowest eigenvalue is of the order of minus constant times lambda squared. That's, of course, the order of magnitude of the depth of the potential well, okay? And furthermore, between the lowest eigenvalue and the lowest eigenvalue plus some constant, there is no spectrum. And that's a very weak assumption. If you think of something like a harmonic oscillator, the second lowest eigenvalue differs from the lowest eigenvalue already by lambda. Okay, so this rules out various evil things that I don't want to talk about. So those are the assumptions on the atomic Hamiltonian. Okay, so those are the atomic potentials, and those are the assumptions on them. Okay, next. Okay, so now we're going to put together a lot of atomic potentials to make the Hamiltonian for the sharply terminated honeycomb. So let's say capital omega is the set of all the sites of a sharply terminated honeycomb. So we fix a straight line, we look at all the sites of the honeycomb structure on one side of the straight line, and we do the following. Next slide. Okay, we form the potential V sub omega of x, which is simply the sum of translates of the atomic potential, where the translates are centered at all the sites that are in our omega, that are on one side of the edge. Okay. And our goal now is to study the Hamiltonian written as h omega lambda. It's minus the Laplacian plus lambda squared times v omega on now on L2 of the plane, and lambda is large compared to 1. So we're looking for large coupling constants, and we wonder how does this Hamiltonian behave? Okay, next slide. Notice, all right, I'm going to do a little elementary Fourier analysis. This Hamiltonian is not lambda h periodic anymore because once you've thrown away half the sites, the structure is no longer invariant under all translations by the lattice. But if the edge is rational, there is still some translation invariance. Next slide. So in particular, there is one vector, V, one non-zero vector in the honeycomb lattice, such that our Hamiltonian is translation invariant under that. Well, all multiples of V, of course, also work. So we take our vector V to be as short as possible. And so let's look at a picture. Next slide. So here is a zigzag type example. In this picture, the zigzag lies, I mean, the structure lies above the line instead of below the line, but this is still a zigzag structure. And notice that if you translate by the vector V, which is the displacement from one dot on the line to the next one, the whole picture is, or at least should be if it were drawn properly, invariant under translation by that one vector V. Okay, next slide. Okay, and therefore there is some corresponding Fourier analysis. A wave function C of x on the plane has parallel quasi-momentum k parallel. That's a real number instead of a vector, if it satisfies the relation shown on the slide. That is, if you translate the wave function by V, the effect of that is to multiply it by the phase e to the I k parallel. If k parallel were 0, this would say it's periodic. And if k parallel is not 0, it's not quite periodic. It's quasi-periodic or pseudo-periodic, I guess. Okay, next slide. Okay, again, as before, L2 k parallel is the space of all wave functions that are pseudo-periodic with respect to the parallel quasi-momentum given, and that space has a natural inner product. Okay, so it's a Hilbert space. Next slide. And as in the study of L2K, we have sort of block theory. Any L2 wave function in the plane can be written as an integral over K parallel of pseudo-periodic wave functions where psi of dot K parallel is a quasi-periodic function of dot with quasi-momentum K parallel, with parallel quasi-momentum K parallel. And again, the Hamiltonian maps each one of those Hilbert spaces to itself. Okay, next slide. And so our goal is to understand the spectral theory of those guys for each K parallel in the real line modulo 2 pi z, which is the natural space of all possible quasi-momenta. And in particular, we want to understand what happens when lambda is large compared to 1. Okay, that's the goal. Now, in order to do this, I want to introduce the back of the envelope calculations that physicists have been making forever. And it's supposed to model what happens when lambda equals infinity. And so part of our job will be to justify this approximation. Next slide, please. Let me check the time. Oh, okay. All right, so a back of the envelope calculation by the physicist Wallace in the 1940s is supposed to give the limit as lambda tends to infinity, but it will involve a parameter called the hopping coefficient, which is completely unspecified. But once you believe that once you postulate a particular hopping coefficient, then this back of the envelope calculation is going to predict interesting stuff. In particular, it will predict that edge states form for sharply terminated honeycombs with zigzag edges, but not with armchair edges. What is an edge state? An edge state is a state in which the electron stays close to the edge for all time and does not diffuse, does not diffract or whatever into the bulk. It just hugs the edge. Okay, next slide. So our results on suitable Schrödinger operators will confirm that the Wallace model gives the correct description for large lambda. It will identify this previously unspecified hopping coefficient, and furthermore, it is an ingredient in the proof of the statement that I made earlier in the lecture that given lots of potentials V, that you can pick just the right coupling constant at which not merely 2 dispersion surfaces meet, but actually 3. Okay, and we will see other strange things coming out from the study of such Hamiltonians. Okay, next. Okay, so let me describe the Wallace model first for graphene without any edges. So for the Schrödinger operator, the state of the system was a function in L2, but in the Wallace model, the state of a system is simply a collection of complex numbers associated to each site in the honeycomb. So for each site omega in the honeycomb, we're given an amplitude psi sub omega. It's just a complex number. And a state of the system is a vector whose components are psi sub omega as omega varies over sites of the honeycomb, and we assume that this vector is in little L2. So that's the Hilbert space on which the Wallace Hamiltonian acts. Okay, next slide. Okay, now what is the Hamiltonian? Well, notice that each state in the honeycomb has exactly 3 nearest neighbors. So if the site is called omega, let's call those nearest neighbors x of omega, y of omega, and z of omega, as in the picture. And next slide. The Wallace Hamiltonian is defined simply by saying that if you apply the Hamiltonian to a vector psi, that's a new vector whose value at the site omega is simply a parameter t, that's the hopping coefficient. We don't know what it is, but it's t times the sum of the values of the given psi at the 3 nearest neighbors. So this Wallace Hamiltonian, except for the factor t, is just the graph Hamiltonian, where you on the graph of all sites of the honeycomb, where you join nearest neighbors and nothing else. Okay, that's the Wallace Hamiltonian. Next slide. Now, just like the continuum problem for the Schrödinger operator, the Wallace Hamiltonian is invariant under translations by vectors in the honeycomb lattice. Next slide. And so therefore, any vector psi, with components psi sub omega can be written as an integral over the Brillouin zone of quasi-periodic states. So K is a quasi-momentum, B is the Brillouin zone, and a quasi-periodic state just means that if you translate by V, you multiply by an exponential factor as shown on the slide. The only difference between that and the Schrödinger picture is that you're evaluating at omega versus omega plus V rather than at X and then X plus V. So it's a discrete version of, all right, well, that's the Wallace Hamiltonian. And so next slide. All right, so the Wallace Hamiltonian acts separately on things of any given quasi-momentum. And so if we fix a quasi-momentum, we can look at the problem localized, so to speak, to that quasi-momentum. And so we're solving the equations in the box. We're looking for the eigenfunctions, and we're looking for the eigenvalues specifically of the Wallace Hamiltonian, restricted, however, to vectors of quasi-momentum K. And we're interested in the dispersion relations, which are simply those eigenvalues as functions of the quasi-momentum K. Next slide. Now, a bit of good news. The space of all psi omega, the space of all states with a given quasi-momentum, is only two-dimensional because, two corresponds to the two colors red and green in my first picture of the honeycomb structure. So this whole space is two-dimensional, and therefore, next slide, the dispersion relations in the Wallace model can be found explicitly by elementary calculations with 2x2 matrices depending on a parameter K that varies over the Brillouin zone. So this instead of analysis, this is just elementary calculation. And so what Wallace found was that there are two dispersion surfaces, and they're given by, so now instead of E1 and E2, I'm going to call them E plus and E minus, and they are given by E plus and E minus are plus or minus T, that mysterious hopping coefficient, times W of K, where W of K is some completely elementary function that I'm not going to write down. But an interesting feature of this elementary function is that it gives rise to Dirac points at the vertices of the Brillouin zone, in particular at the point capital K. Okay, next slide. So that's the Wallace model for the bulk. So, okay, we're going to return later to discuss the Wallace model for graphene with an edge. Okay, but for the moment, let's just think what happens for Schrödinger operators as opposed to the Wallace model when lambda is big. Can we justify the Wallace model? Okay, next slide. So we can ask, what's the relation between the Wallace model and the Schrödinger operator? Well, I guess that should be a lambda squared. Anyway, and also, what's this hopping coefficient? What should T be in order to make the Wallace model correctly predict what the Schrödinger operator is doing? Okay, here's the answer. All right, so to state the answer, I need to introduce the ground state eigenfunction for the atomic Hamiltonian. Remember, before we made the Hamiltonian for terminated graphene, we talked about a Hamiltonian for a single atom, and it's minus Laplacian plus lambda squared VA. Let's say P sub lambda of X is the ground state normalized to have L2 norm 1. So that will play a role. Okay, next slide. And now let's let K going to E plus of K or K going to E minus of K, let those be the two lowest dispersion surfaces for H lambda. So of course, H lambda has infinitely many dispersion surfaces, but we're going to look at the lowest two. Okay, next. Okay, Well, the next theorem says that for a suitable energy, E0 lambda, depending on lambda, we have the statement on the slide, namely, if you take these two lowest dispersion relations and subtract that energy and divide by rho lambda, I'll tell you later what rho lambda is, that tends to plus or minus W of K as lambda tends to infinity, where, okay, next slide, W of K is precisely Wallace's elementary function, and rho lambda is equal to the integral that you see on the slide, where V is as in the picture, namely V is just any one of the three possible, or I guess of the six possible vectors that join a honeycomb site to its nearest neighbor. And so that's the definition of rho lambda. And so what it means is that if we look at the Schrödinger equation, if we translate the energy, and if we rescale the energy by this quantity rho lambda, then we get Wallace's Hamiltonian, and so I'm sorry, Wallace's dispersion relations. And so it means that we have justified Wallace's calculations, and we have also identified the hopping coefficient T. It is equal to this rho lambda. Okay, next slide. Okay, so yes, rho lambda is the hopping coefficient in the Wallace model. Next slide. Okay, also, if you look carefully at the statement of that theorem, you see that it doesn't quite prove that a Dirac cone forms, but indeed a Dirac cone forms. So that's also part of the theorem. And there's the precise statement on the slide. Okay, next slide. Okay, so much for theorem 3. Okay, onward. Next slide. Okay, so now let's get back to sharply terminated honeycombs. And so what we're going to do now is look at both the Wallace model and the Schrödinger equation for sharply terminated honeycombs. Let me check the time. Maybe it is conceivable that I'm actually ahead of time this time. Okay, so all right, here's a picture of the sharply terminated honeycomb. Remember, there's a straight line in the plane. I'm going to take it to be a rational edge. And on one side, we have red dots. Those are the atoms that are present. And on the other side, there are green dots. That's where atoms used to be, but we have removed them. So those sites are vacant. Okay, next slide. Okay, so let me introduce the Wallace model in which there is an edge. So now a wave function, psi, will be a collection of amplitudes, psi omega, where omega now varies only over the sites of the terminated honeycomb. And each psi omega, again, is just a complex number. But now, when there's no atom, there is no amplitude. Okay, next. What is the Hamiltonian? Well, for omega, any site in the terminated honeycomb, we define h psi evaluated at the site omega by the same formula as before, but we delete any psi's that arise from the unoccupied sites. So for example, okay, next slide. Here's a picture. In the red dot, in this picture, the red dots are sites which are present in the terminated honeycomb, and the green dots are sites which are not present in the terminated honeycomb. They have been removed because they're on the wrong side of the blue line, which I haven't drawn. Okay, so to evaluate the Hamiltonian at psi at the particular site omega, we would like to sum psi at x of omega, y of omega, and z of omega, because those are the three neighbors of omega. But z of omega is not present, and so the formula is simply given as on the slide. And so again, h is simply the graph Laplacian of the nearest neighbor graph for the terminated structure, multiplied by this factor t, the hopping coefficient. Okay, next slide. Now, if our edge is rational, in other words, it passes through two distinct points in the honeycomb, then the Wallace Hamiltonian and the Schrödinger operator are both still invariant under translation by a vector red v in the honeycomb. and we're going to take that vector to be as short as possible. Okay, next slide. Okay, and therefore, as before, this is maybe the third time I've said such things. Therefore, any state can be Fourier analyzed. It can be written as an integral over parallel quasi-momenta of pseudo-periodic states, which transform as shown under the action of translation by this vector red v. So in the Wallace model, that just means that if you take a site and translate it by v, the amplitude changes by a phase factor. And if you are instead looking at the Schrödinger operator, it means that if you evaluate the wave function at the translative x by the vector v, that changes by the phase factor. Okay, well, the Wallace model that is sharply terminated along a zigzag edge gives rise to edge states. Okay, next slide. Okay, and so here's what happens. For parallel quasi-momenta between 2 pi over 3 and 4 pi over 3, the Wallace Hamiltonian has an eigenpair, E and psi, depending on k parallel, where, okay, the psi has parallel quasi-momentum given, and furthermore, the amplitudes decay exponentially fast to 0 as the distance from the site to the edge tends to infinity. And furthermore, the eigenvalue E is precisely 0. So this is what's called a flat band. Okay, next slide. So here's a picture. So for any rational edge, we're going to be drawing a picture like this. Let me explain what the picture means. So the horizontal axis is the parallel quasi-momentum. On the vertical axis are energies E, and K. Since K parallel is a point of R2 mod 2 pi integers, it's enough to look at 0 to 2 pi. Now, if you fix a parallel quasi-momentum, that means you're fixing a point on the horizontal axis, and through that point you should draw a vertical line. And if you draw that vertical line, then the intersection of that vertical line with the stuff-colored red represents the spectrum of the Hamiltonian for the terminated structure localized to quasi-momentum H. And so notice we have continuous spectrum, the hatched region. We have some white space where there is no spectrum, but we have this very interesting horizontal red line, the flat band. Those correspond to edge states. Okay, that's for the zigzag edge. Okay, let's look at the corresponding picture for other classical edges. Okay, so next slide. So the Wallace model sharply terminated along an armchair edge gives rise to no edge states. So let's look at the corresponding picture for an armchair. Next slide. Here it is. And again, we've got continuous spectrum outside of some funny shaped region that I seem to have drawn not quite right, but close enough. But notice that there is no horizontal red line, there is no flat band, and indeed, there is no spectrum at all other than the continuous spectrum. Okay, next slide. Here's now the bearded zigzag, the third classical example, does give rise to flat band edge states, but those edge states are at precisely those quasi-momenta for which the unbearded zigzag does not give rise to flat band edges. Let's look at the picture for the bearded zigzag. There it is. Okay, so again, it's not the world's most accurate drawing, but you'll notice there's continuous spectrum and then a lot of white space between pieces of the continuous spectrum, which is resolvent. But there are these horizontal red lines, flat bands corresponding to edge states at precisely those quasi-momenta for which the unbearded zigzag did not give rise to edge states. So that's a little weird. So there are these three pictures. Okay, next slide. Okay, so now I want to talk about the Wallace model for an arbitrary rational edge, okay? And we're going to be talking about flat band edge states and continuous spectra. And as far as those are concerned, okay, next slide, the only three pictures that can possibly arise are exactly the ones that you've just seen. No other pictures arise. No matter what the rational edge is, you will always get exactly one of those three pictures, not sort of like or topologically like or exactly those pictures. Okay, and furthermore, by doing some bookkeeping, one can decide in any given case which of the three pictures applies. Okay, so that tells us about continuous spectra and about flat band edge states. Next slide. However, there's more to the story because it seems that most rational edges give rise to non-flat band edge states also. That is, if you look at the Wallace Hamiltonian, then it has discrete spectrum other than at E = 0. And let's look at a picture. Next slide. And so here's a picture of something that would have been like the armchair. As far as the continuous spectrum is concerned, there is stuff above and below some funny lens shape. There is no horizontal red line, but there are two curved red lines. Those are the non-flat band point spectrum, and they give rise to edge states of non-zero energy. Okay, and furthermore, the number of those lines seems to grow as the edge gets more complicated. Okay, so there are more things in heaven and earth than dreamt of in the previous philosophy. Okay, next. Okay, here's another picture. This sort of thing can happen also, and it does. Okay, so in this picture we have a continuous spectrum. We have the red horizontal line of flat band edge states, but we also have non-flat band edge states in the region where there were no flat bands before. So that's another picture. Okay, next slide. Now, truth in packaging, the results on non-flat band edge states are based on numerics. Everything else I've said has been rigorously, proven, but the non-flat band edge states are based on numerics, not a rigorous proof. But we've been in discussions with Javi Gomez Serrano, and he is optimistic about making a rigorous computer-assisted proof, and I think he knows what he's talking about, and I wouldn't be surprised if in the next few months the computer-assisted proof appears. Okay, next. Okay, well, so that takes care of rational edges. What about irrational edges? Even in the Wallace model, they are completely mysterious. Do they give rise to edge states? Nobody knows. Okay, so it would be nice to have some theorems about irrational edges, and of course we are considering looking at our results for rational edges and taking the limit as our rational slopes approach an irrational slope, but so far it's all wishful thinking. Okay, so much for terminated honeycombs in the Wallace model. The next thing to do is to look at, okay, next slide, Schrödinger operators for sharply terminated honeycombs. Okay, so next slide. So for a rational edge for which the Wallace model predicts a flat band, okay, let's fix an atomic potential as in our previous discussion of terminated stuff. I guess it was called VA before, now out of lack of consistency, it's called V0. Okay, so we fix such an atomic potential. Okay, next slide. We form the natural Hamiltonian arising from the terminated honeycomb minus Laplacian plus this potential with the coupling constant lambda squared and copies of the atomic potential translated to all of the sites of the terminated honeycomb. This acts on all functions psi of x that are pseudo-periodic with period k parallel as shown on the slide. Okay, so the last theorem of the talk is this: fix a k parallel for which the Wallace model predicts a flat band edge state. Then if the coupling constant lambda is large enough, the Hamiltonian has an eigenpair where, next slide, where again the wave function tends to 0 rapidly as the distance from the edge tends to infinity. It's exponentially fast. Okay, and the eigenvalue is equal to is equal to a constant value independent of the quasi-momentum plus an error which is exponentially small even compared to the hopping coefficient, rho lambda. And so we get not an exactly flat band, but a nearly flat band, exponentially close to flat, even on the length scale in which we could see the Dirac cone emerging. Okay, next slide. Now, very likely our methods yield an analogous result for those non-flat bands for the, so when the Wallace model predicts an edge state of non-zero energy, very likely our methods prove also that there exists an eigenpair for the Schrödinger operator for which the state tends rapidly to, where the wave function decays very rapidly away from the edge, and where the eigenvalue is exponentially close to the one predicted by the Wallace model on the scale of the Wallace model. But all right, very likely our methods do it, but we only discovered rather recently that these non-flat bands exist, and so we haven't yet put in the work to check it. I would be surprised if there's an obstruction, but we haven't done it. Okay, next slide. Let's stop here. Thank you for listening. I hope you enjoyed the talk. Let's see what time it is. Okay, I was supposed to finish in 55 minutes, and I have, for once, finished in 53 minutes. Okay.
Thank you very much, Charlie, for the talk. So it's now time for questions, for comments, for remarks. Anybody in the audience want to add something to the talk? Antonio?
I won't ask about the question with magnetic field, but
okay, we can discuss that offline, as we have done before.
Okay, but listen, suppose that now we have, this is a more general question, not only for graphene, but we have a solid state, a crystal, and so on, the block electron, then we have the strong binding regime. Then we have the limit is the type version of the Wallace. It's well known that the limit, the the semi-classical lambda tends to infinity or whatever of the strong binding converges to the tight binding regime in general.
What a good question.
Somehow the solid state physics is based on a statement like that.
Like that, yeah. So let's see what was known. Let me think. So unfortunately, it's been a while, so I have to jog my memory. There are classical results. All right. Oh, okay. I think I remember. Here is the situation. The classical. All right. So one can ask two questions. What is in the literature, and what could easily be done by the same techniques? Let's ask the first question first. Okay. Now, the classical literature, I believe, discussed only the square lattice, probably for no good reason. Okay. And so there are, all right. In that case, the semi-classical literature assumes that the potential is C infinity, and maybe it has a non-degenerate minimum at the origin. Okay, the atomic potential. Okay, and in that case, semi-classical analysis for a for a square lattice, I don't think it's sharply terminated, but I could be wrong. The eigenvalues are well described by semi-classical stuff. That is fundamentally based on the assumption that that the potential is C infinity, because it's semi-classical analysis. Okay. Now, all right. Presumably, if they had the interest to do so, if they, I mean, the semi-classical analysis precedes the excitement about graphene. If they had wanted to, I'm sure they could have done the same thing for the honeycomb lattice or for more general things. Okay. Now, let's talk about our result. Our result deals with C infinity functions, but that's just out of laziness. And we could, for example, include Coulomb singularities or more general things. And in that case, it would be easy for our techniques to apply, but we were too lazy to do it. Okay, so.
Okay, thank you.
Okay, sure. Okay.
Any other question or comment? So I don't know if anybody attending through Zoom has some comment.
May I ask a question?
Yes.
Oh, you hear me, great. So I'm not sure if my question makes sense in terms like physically, but still I think mathematically you can ask it. So in the Wallace model, right, you started describing the honeycomb model. So you have sites of two different flavors, right?
Mm-hmm.
And the Wallace model doesn't see it, right? So this hopping parameter, you look at all the neighbors and you think of all the neighbors as being of the same flavor. So can you modify this model to?
Well, okay. You can modify the model, but if you look at the picture of the honeycomb structure, all three neighbors of a red point are always green points, and all three neighbors of a green point are always red points. So the only distinctions that you would make would be.
Yes, so maybe you have.
I'm sorry. You want to modify the problem. You want to modify the problem.
Yes. So if you're a red point and you see only green neighbors, maybe you have one parameter, and if you're a green point and you see only red points, maybe you have a parameter. I
see. Oh, okay. That's reasonable.
Maybe it doesn't make sense physically, right? Because we assume some symmetry of the forces, but still.
Okay. I could. Well, let's see. All right. So I don't know whether one could make a physical, whether one could realize that physically. I think maybe you are better placed than I am to find out about that. But certainly one could analyze it mathematically. It would be no harder than the Wallace model. My guess, just a guess, is that it gives rise to Dirac points also, because one could perturb, one could perturb the classical Wallace model to a thing like that, and allegedly Dirac cones are supposed to be robust to small perturbations as long as the potentials are even. So, oh, wait a minute, but wait. So is this potential even? It's not clear. So if you look at a red point and its nearest neighbor green point, the hopping coefficient from the red point to the green point is not equal to the hopping coefficient from the green point to the red point. Maybe that means that I should not expect a Dirac point. Maybe all I should say is one could set up the model mathematically. One could analyze it by the same kinds of elementary calculations as Wallace did in 1940 something. And exactly what the consequences are, I don't know.
Okay, thank you.
Sure.
Any other comment or question from the people attending through Zoom?
I would like to make one comment at the end. I have enjoyed many times visiting the ICMAT. It is a lot more fun to visit in person than it is to visit by Zoom, but I'm glad to have visited today. I have profited mathematically a great deal by my visits to ICMAT. And so if you have enjoyed these lectures, I'm giving a little bit back. So thank you all.
Thank you. Thank you. Okay, so I think it's time to finish this meeting. Thank you very much for these two beautiful talks and for spending your morning and our afternoon, evening with us. It's been a great pleasure to have you here. Not physically, but we know that you've been here many times. We hope to have you pretty soon. So thank you everybody for coming. Thank you the people attending through Zoom or using YouTube. And we see each other very soon. Thank you.
Bye-bye.